So let's continue with the third question. Now, we've designed a p-type controller in the previous question. Now, the question is to come up with a lag controller that halves the velocity tracking error, which means that if we apply ramp type inputs, the steady state error should be the half of it. So lag controllers especially are designed in order to increase the performance of steady state behavior. And the aim here is to, if possible, not to change the transient behavior. So we shouldn't touch the transients, but in steady state, our controller or lag controller should increase the performance by, for example, halving the velocity tracking error. So there are three types of error constants. One of them is the velocity tracking error, which is given here. There is a position tracking error, which corresponds to step type inputs. So the steady state error and the controller that does that for step type inputs is the position one. The velocity is for ramp type inputs, and then there's also acceleration type tracking error, which corresponds to, well, the parabolic inputs. So yeah. Now the definitions are pretty straightforward of those errors, and you can work them out by examining the steady state. So using the final value theorem, you can work your way out. So let's copy the system, and possibly also k-val will be necessary. So we'll come back to that later. So there are two, again, methods that we will use, one of them being the frequency domain. So how can we design a lag controller using the frequency domain? And how can we design a lag controller that does the same job with time domain? So this is basically it. Now, for lag type controllers especially, the time domain approach will be probably faster and better to understand. So I recommended that designing a p-type controller for only overshoot requirements is better done in frequency domain. But here I would suggest that using the time domain would be a bit more time efficient. We'll see. Now, how can we design the frequency domain using the frequency domain? Now, first of all, we need to find what the steady state error for ramp type inputs is, or what our constant is in this case. So, by the way, the constants, the velocity constant, the position constant, and the acceleration constant are just defined to calculate the steady state errors. So, yeah, they are basically helping definitions. And so how can we compute the velocity constant and therefore the velocity error? So the formal definition is the limit of s tending 0, so s tends 0, and the limit s times the loop transfer function, basically. So this should give us the kV, the velocity constant, and the steady state error for ramp type inputs is related inversely to kV. So that's basically it. This is the definition. For the position constant, we don't have s here. So for acceleration, we have s squared, etc. The relation for the position one was, if I'm not wrong, you should look it up in your lecture notes, but it was 1 divided by 1 plus k position, and then we have again 1 divided by k a for EA, I guess. So yeah, you should have a table that sums this up. Unfortunately, I didn't add one here, so yeah, you should really check it out. But for this question specific, we know that this is the limit that we should calculate, and then this is the error that relates to this coefficient. Now basically, we have already a design, and let me just check out what the k value was. It was 1.24 4, 3. So let's take this one. So the question tells us that we have a certain k value, let's say kp, which is the p-type controller, and then we have gs. Now, remember that this ls is the loop transfer function, and the closed loop is defined as ls divided by 1 plus ls. So from the loop to the closed loop, we use this relation here. So therefore, my loop transfer function previously was kp times gs. So keep that in mind. So this limit should be calculated for the limit of s times kp times gs. So that's important. Now, once we have that, what we're looking at basically is the following: kp times gs. So this is ls, and we should look for this limit. So let me comment this out and use here GSS, and this should be LSS because I'm using the symbolic. I'm going to use the symbolic expression here. There we go. So, or we could also use ls, doesn't matter. Let me just use this one here. So here, if we multiply with s, you can see that here we have also an s in the denominator. So we will get rid of that. So, and plugging s here equals 0 would get rid of that. We would get 7.466 divided by 6. So that's basically our constant that we are looking for. 7.466 divided by 6. There we go. This is basically the constant that we are after. And you can also see that this is basically the p-type controller that we have here. So usually for the position constant, what we use is we use directly s equals 0. Now for this, we can see that plugging s equals 0, or taking this limit here. So let me copy this. And let's see what happens. So we have the position constant, we don't have this s, and plugging in this here, looking for this limit here, results in infinity. So the position constant is infinity, which then shows us that 1 divided by 1 plus infinity should give 1 divided by infinity, which should give us 0. So 0 EP, which is the steady state error. For this system, using a p-type controller results in 0 steady state error for step type inputs. And the way that this works is that we have a type 1 loop transfer function here. So the type of this is 1. So it means that we have a pole at the origin. So this is basically the magic here. So it's not the p-type controller, it's the integrator in the loop transfer function, or the pole at the origin of the loop transfer function that achieves the step type input tracking with 0 steady state error. But of course, if you're tracking one type of input with 0 steady state error, it doesn't mean that you will track all the inputs. For example, for this system, we are not exactly tracking the ramp type input, but we have a certain constant, and then taking the inverse will tell us how much error we will have in the ramp output. So that's basically very much important in this case. So we can directly conclude that 1 divided by kp is our velocity error. And let's check it out. Let's see what it is. So it is 0.8037, which means that there will be an offset of this value. So there will be two ramps, and one of them, being the output, will have a slight offset. So that's basically what it means. In order to be able to track this, you would need another integrator, which would cause kV to be infinity and EV to be 0. So the more let's say the integral, the more you have the integral in the input. So you have impulse, step, ramp, and then parabolic. So if you're going one stage up, you will need another integrator in order to keep track of zero tracking error. So therefore, if you want to track higher order, let's say, type inputs, meaning step, ramp, and parabolic, you need one more integrator. So the type of the system determines basically what you can track and what you cannot. Now, in our case, we want to halve this error. We are aware that we cannot completely track the input, but we want to have a better result, slightly better than this one here. So since the relation here, by the way, this should, okay, this is KV, and we should have this error here. So looking at these two definitions here, one of them being the limit and the other one the error itself, what do we need in order to have half error? So it is quite obvious, and it should be quite obvious, that KV should be 2 times more than it is to achieve this. So if KV is double, then EV will be halved. So therefore, our lag controller should contribute a gain of 2. That's basically it. So the gain of our lag controller, let's say the apps value of Fs, which will be the lag controller. So design a controller that has absolute of 2. That's basically it. Now, how can we define this and use the frequency domain method? Because first of all, we are using the frequency domain method. So how can we use the frequency domain method and combine this? So yeah, in order to design the lag controller, what we have to do is we have to get the plant that we want to use here. Now, our plant originally was GS, but we added a p-type controller, which is still there, and we need to add another gain, or the gain part of our lag controller, because you can write the gain controller as follows. You can use s plus z and then divide by s plus p. So this is one way of defining this. So this k should be equal to 2. So all the lag controllers that looks like this are my concern here. So therefore, my loop transfer function that I want to achieve here looks like this. So 2 times the controller given here, divided by s plus p, and then times kp, and then times gs. So I know what kp, gs, and 2 is. So if I combine them and rewrite this equation like this, it is the equivalent of designing another controller, another lag controller, to a certain other plant, let's say HS, where HS is defined as this multiplication here. And by the way, if you're using the time domain, you will use this notation here, k times s plus z divided by s plus p, because in the frequency domain, we don't talk about zeros and poles, but we will come to that in the second part. But if you remember, in the root locus method, for example, in the time domain, we use zeros and poles, we place some poles and zeros, manipulate the root locus, and then achieve the controller or the control that we want. But here we don't talk about zeros and poles. Therefore, we have another definition that we can use here. And that definition looks like tau times s plus 1, and then tau times s plus 1, but with a certain alpha to it, which is basically the frequency domain equivalent of our controller definition. And here this ratio and the tau will determine the characteristics of our controller. So we can look for z and p, or also k, in the time domain, or we can look for tau and alpha in the frequency domain. And you can convert this by dividing to the constant terms that you need here. you can normalize this so that you have this relation here. That's pretty much it. Now, therefore, instead of using the body plot of GS for part A, we will use this body plot here and go through our design algorithm. So let's get rid of everything here. We only know what KP is, and we will define another transfer function HS that looks like this. So we are trying to design a controller that has, by the way, gain 1, because we don't want to mess up the gain of this loop transfer function. If we do that, then this limit will change, KV will change, and then the error will change. We don't want that. We have already calculated what the gain should be, and we've adjusted accordingly. The only thing that is left here is to determine what alpha and tau should be, and that's it, basically. So yeah, how can we do this? For this to be possible, we need the zeta value here. Once you've designed your p-type controller, you would have these already calculated. And we also need this one here. And maybe I can also go ahead and copy this part here too, because that's also necessary. So let's take this part too, maybe this part too. So basically we will somehow repeat this process, but we will look for different outcomes of the body plot. So I assume that we have already designed our KP. Therefore, we need to bring this up somewhere here. And there we go. Now, we have the zeta value, we have the corresponding phi value, and we have also the limit and the corresponding HS. Now at this point, we will look for, again, this phase value here, but let me show you something. Now let's look at this problem. Now I'm looking for Fs, which is defined using alpha and tau, and I have Fs times Ls, or Hs in this case, it's identical. Let's say Hs. So, and my closed loop will consist of this here divided by 1 plus this. Hope that this makes sense. Now I have modified my plan so that it meets my requirements to a certain degree, and then I have alpha and tau, which defines Fs. So tau s plus 1 divided by alpha times tau plus s times s plus 1 is Fs, and I have this one here. So you remember we were checking for F times Hs being equal to -1 for omega. Let's say F omega and H omega, S equals J omega is plugged in here. And we concluded that the absolute value of this and the argument of that should be equal to 1 and then minus 180 degrees. Now then we talked about the fact that if we have minus 180 degrees, we will have exactly zeta equals 0. So that's not what we want here. We want to have a certain zeta value. So for that zeta value, we should include a certain phi m, a phase margin. Now this phase margin will then hopefully be used to come up with the corresponding alpha and tau values, or the p-type controller in the previous case. Now, and I've also talked about the fact that we can expand this argument such that this is the equation that we have to consider. Now, usually, the argument of the controller is 0 for p-type controllers, and this term vanishes, and then we look for the body plot and look for this angle condition. But in our case, it's not the case, because F omega is indeed tau times j omega plus 1, and then the same with alpha. And it is depending on omega. And it has a certain angle contribution, hopefully less than, so a negative value, hopefully. And that's basically it. Now, we didn't mention the time domain design of the lag controller, but the argument that I'm going to make is, or the assumption that I'm going to make is the following. I assume, and we will see why, I assume that the angle contribution here should be hopefully less than or equal to 10 degrees. So something like this. Now we will come back to this. If you think about this upper limit, which is just an intuitive limit, it's not really a theoretical fact, but there should be an amount of degree here, and we shouldn't surpass that, basically. So there's an upper limit to this, and it should be a low one. So let's say 10 degrees. Let's say that the argument, the absolute value of the argument, because it will be negative, because it's lag type controller. So let's say the absolute value here should be less than 10 degrees. So if I have such an assumption, I will see that I might do something like this. Let's say it is minus 10 at max. Then this will come to the right side, and I will get something like this here. So this is still a simple requirement, and I can look for, because I know what phi m is, I know that I should calculate this phase angle, and I could use that angle and determine a certain omega value. Now, if I have this omega value, and if I go through the design process, once I have acquired my controller, I can come back to this and check if it's true or not. If it's true, then I have a certain approximation of the design. If not, then I should reconsider it. So I could iterate here. I could choose 20 degrees and then add 20 degrees and come up with a result, and then try it over and over again. And it will hopefully converge to a point where I have the exact solution, because it's not really easy to overcome this argument here. So I have a certain assumption that the angle of this controller should not be too large, and if that's the case, then I will solve this. So based on this assumption, I'm going to look for this angle here. So instead of having this, I will have a safety margin, which should be greater than the controller contribution in terms of angle, hopefully. So for this reason, I will, by the way, if you think about it, this should be around omega, because omega star should be the point there where this should be satisfied. So if I have omega star, h omega star, I'm looking for omega star. So at omega star, this should be the case. So let's have this commented out. So there we go. Now, the only difference, and it should make sense if you think about it, the only difference here is that I'm adding a certain amount of degrees to my phase angle. And I'm assuming that it should be less than or equal to 10, which should mean that the closed loop should have almost the same phase angle, or hopefully exactly the same, because if the controller gets rid of 10 degrees, if it's contributing negative 10 at that frequency, then I should have basically the same phase. And with the same phase, I should have the same overshoot, because the same phase means that I have the same phase margin, I have the same zeta value, therefore I should have the same overshoot. So the overshoot should not change if my controller has almost exactly 10 degrees contribution at that frequency. So I hope that this makes sense. Now I'm adding 10 to it, and I'm going to search that point on the body plot. But be careful, I'm not using the actual plant, but I'm using the modified plant, which I've defined here, which is basically 2 times kp times gs. Now you could also use the actual body plot. This might be the case for the final exam questions, because it is a tradition to use it like this, but you have to modify the results yourself. So think about the body plot that is given to you. Let's say figure body GS. You're given the following body plot, but you're asked to do a design question 3, or to solve question 3. Now here the angle condition does not change, so we have the same phase angle even if I have HS, but the phase graph here will change, obviously. So let's also demonstrate that. So let's say this is the original one, and then I have HS, which should be in red, and let's see what the difference is. So there we go. You have the same phase plot, but your angle plot is slightly modified. And since you're in decibels, it doesn't even move that much, but actually it moves. But in decibels, that's a small effect. So you can safely use the same phase plot and search for the frequency, but the gain value would be a bit different. So you have to take this part into account. Basically, you have to multiply by 2.4886. So yeah, that's the tradition. If you prepare an exam question, most of the time you require the student to see this kind of stuff. So now let's stick with the phase plot of GS and the magnitude, and then let's also modify it ourselves. So I will get the phase and magnitude that corresponds to the desired phase angle, and I will have omega, mag val, and phase val. So this is basically what I've read from the body plot. I looked for this phase angle, I got the frequency 0.68, and then I have this magnitude 1.2 approximately. But this is actually not the gain itself. So once we've acquired this point, by the way, alpha is straightforward and is defined as the absolute value of G omega at omega star. And then tau is less than or equal, but I will use equal here, is 10 divided by omega star. Actually, this is less than or equal, but let's take it equal. This is maximum tau. So these two equations give you the lag controller that you need. And that's basically it. The frequency methods are always the same. You have some theoretical aspect, and you use that aspect, read some values of the phase plot or magnitude plot, and you use these relations and you're good to go. This is much, much different than using the time domain approach, where you have to calculate everything in detail. You're just taking a rough approach, you have some assumptions, and that's it. But you have to know what you're doing, basically, and you have to be aware of the potential errors that you could make. So that's the challenge here. So yeah, let's try to calculate them. Now, in order to have alpha, I will have this, but the actual value that I should have is h omega. And there is a static relation, so I could directly substitute this one here. So instead of calculating h omega's magnitude, I can calculate 2 times kp times the value that I've read on the body plot. So that's basically what I'm going to do. So 2 times kp times the magnitude value that I've basically calculated. So it should be equal to 3 point something. So nice. And we will have tau, which is basically the same because it does not rely on alpha. So omega val should give us that with omega val. Now, at this point, I'm ready to define my controller, and the controller should be the following. Tau times s plus 1, and then alpha times tau times s plus 1. Now, let's basically run the script one more time. And fs looks like this. So alpha seems to be 3 something, and tau seems to be 14.71. So before I continue, I could convert this into symbolic expression and plug in the omega star and see what the result will be. Let's do that. Let's substitute into, let's create FSS, which can be created quite easily. Tau times s plus 1, and then alpha times tau times s plus 1. So I've created it. Now let's substitute into Fs, instead of s, j times, or 1i times omega val. Since that's the, let's say f val, since that's the frequency. And it should be a double value. Let's check that. And not including k is not really important in terms of the argument here. So f val is a certain complex number. Now what is the angle of this? It is 0.06. Now I guess there's also angle d in degrees. Oh, seems like not. So angle should be in radians. If I convert it back into degrees, it is 3.8 degrees. And it's negative because it's a lag controller. So my assumption holds. I assumed that it should be less than or equal to 3. I assumed that it was 10 at max, and I've found out that it is less than 10. So what I can practically do, I can update my assumption to lower limit. Instead of 10, I might use 5 and use that value. But before I do that, let's look for the closed loop and see what happens. So my closed loop here, let's have two different closed loop transfer functions. One of them should be kp times gs, 1, basically the previous one. And then we have ts2, which is the feedback of 2 times fs times kp times gs, 1. Now why? Because I didn't include the gain of the lag controller into the definition of fs, which is this one here. You could also say this is 2 times and then get rid of this part. But we have the lag controller with 2 times the velocity constant, and then we have the previous p-type controller and then the plant itself. So let's look for the step response of ts, which is the black one, and then ts2, which is going to be the red one. So as you can see, there's a slight change. It has an effect on the transients, but the overshoot remains almost the same. It is about the same vicinity of 30% overshoot. But I'm really not interested in the step response because the design was for ramp type inputs, because we used the velocity constant and velocity error. So how can I switch back to ramp type inputs? Now, if you remember in the previous lectures, I told you that you can use the step function, but you have to include a S term to end up with the ramp response. So I don't remember if there's a ramp function. Seems like it. So there's no ramp function. You could use LSIM, but I don't want to overcomplicate stuff. But since we deal with LTI systems, I can basically include a integrator, because if I take the integral of the input, the output will still be integrated. It will not mess up. So I could just say Okay, this is basically figure 1. But what about the ramp type inputs? I can also check that by taking the integral 1, 0, which is 1 divided by s, and hopefully it should give me the ramp response. Of course, I should change this to 2. Let's clear. So there we go. Now we have the ramp response, but it seems that it is basically close. But let's see what the transients are at the start. Now, eventually, it's quite hard to calculate what the difference here is. And we did use it, okay. Eventually, you can see that the ramp function here is a bit higher. Now, we might do something like, so it's 1200s. Maybe we should limit the time here a little bit to, let's say, 10 seconds. 0.01 up to 10 seconds. Now, I'm not sure. Let's use help, but I'm not sure if I'm going to be able to give it multiple systems and time at once. Let's see. So we can give multiple systems, but not time vectors as far as I can see it. So we have to do it manually. Let's quickly get rid of that. Let's do it. So y comma t should be equal to step of the following. And then the second output should be y2 and ts2. Get rid of that. Plot. Let's plot t comma t, which is the ramp function basically, with line width of 2. Let's make it a different color maybe. Let's say magenta for some reason. And t comma y should be k, and t comma y2 should be red. And that's basically it. So 1, 3. Maybe grid on and hold on should be helpful here. Hold on, grid on, CLF also. So now we can see that there's more difference here. And you can also see that the red one is closer to this color, this magenta color. So it seems like we have a closer response, and I'm not sure if it's the half because it seems to be more optimistic, and it seems like it is far, far better than what we've tried to achieve here. And the reason behind that is probably this value here, this assumption being less than or equal to 10. So let's update it a little bit. Let's say we have found out that the angle times 180 divided by pi of fs, let's see what it was. So it was of f val, of course. So So let's see what it was. It was 3.8. So we might assume 5 degrees here. Not exactly that, because it will maybe change. So let's have 5 here, and let's also use, where is it? Yeah, 5 in here. So let's see what the result will be. So this is not really necessary. So you can see now our assumption does not hold. So a little higher limit, let's say 7 maybe is a good approximation. Let's try it again. So 7 seems to be exactly the value. So still our lag controller has way better offset, way less offset than the actual input, because magenta was the input and red was the second design, and the first one was this. So we can see that we have improved the performance in terms of ramp response tracking immensely. So this is basically it for the frequency domain approach, because this is the maximum that we can do here. So, of course, this should be equal to 7. Maybe there's still some stuff to do here. Yeah, you can see that you will eventually end up in a point where you have exactly the value that you used here. So 7 is a bit too much. Use 6 and iterate through it. But if you're on an exam, I would recommend you to use 10. Then check if your controller holds the assumption, and you can leave it there, because we have MATLAB and we can do it over and over again, but in the exam you would basically not do it. So, and we didn't touch too much the overshoot value. It is even closer now. So now how can we design the same controller using the time domain approach? Now here the time domain approach is even better, because we still have the assumption that the gain of our controller should be equal to 2. So we will have to have the same conclusion, because we will use again this set of equations here, the limit and then the inverse of kV. And then we will conclude that Hs should be 2 times Kp times Gs, or our controller should have gain 2. Now let me state it in the time domain. In the time domain, we will most practically use K times S plus Z divided by S plus P, and you can get rid of this K, because the this should be P. Now in the steady state, this becomes K times Z divided by P. So it's really not necessary to provide any K, because you have Z divided by P. So if the gain of the controller should be equal to 2, and if you fix this to 2, then Z divided by P should be equal to 1 in this case, because you don't want to mess the gain value here. So omitting this is a better idea here, since we will have Z divided by P as the steady state gain, and that should be equal to 2. Why? Because we want to double the velocity constant to halve the velocity error. So therefore, this still sticks here. And now at this point, in the pole zero map, we assume that the added pole zero pair should not change the root locus too much. So what do I mean by that? So I want to use the root locus plot, and we have already Kp times Gs. Now, so therefore, maybe we should use Ls, which is Kp times Gs, which is the previous loop transfer function. And we use the loop transfer function for the root locus plot. Remember that we use the loop transfer function, not the closed loop transfer function, because that's most of the time what confuses the students, as I've seen from the previous work. Now, it is Ls, and if you are using the open loop, this becomes Gs. So root locus of Gs makes sense. if you design a controller and have some poles and zeros added to the plant, that becomes LS, not TS, which is the closed loop here. So certain zeros, let's add a zero here, let's add a pole here. This times this is still the loop transfer function, and you should look for the loop transfer function root locus. So something like this makes only sense if the formed closed loop is another plant for some other control structure. So this doesn't make sense if you're finished at TS. If you still want to have another controller that is on top of this closed loop, then you might look for TS, the root locus of TS. But most of the time, this doesn't make any sense because this doesn't contribute to the control design that you've just carried out. If you added some poles and zeros to your plant, then LS, and you should look for LS. So therefore, we should look at LS, not at TS. So this is the previous design, and this is the loop transfer function from the previous design. And we have the root locus given here. Now, what we want to do is we want to add gain 2 to it. So let's say LS2. Now this is 2 times LS, but we still didn't determine what the pole 0 pair should be. But we could choose any pole 0 pair that satisfies this equation here. For example, choosing P equals 1 and Z equals 2 could be one solution. So we might try that out. And let's try it out. Let's say TF and then 1 Z and then 1 P. So let's say P val and Z val. So let's get rid of this. So there will be a certain Z val and a certain P val. Now, if we choose, for example, P val first, for example, being equal to 1, we could safely assume that 2 times P val would be the solution of this equation. So I have a parameter P val, which I can change over a range, and I can end up with a controller. If you go ahead and use the polynomial coefficient equation approach, the algebraic approach based on the polynomials, then you will end up with a problem that has one free variable that you can vary over a certain interval. So this is basically a 2 equation, 3 unknowns type of problem here. So you will conclude the same here. Now, since I have P val equals 1, this would change the root locus of the system, and let me demonstrate that by using basically the root locus plot here. Let's say the black one should be the previous one, the red one should be the new one. So let's see what happens. So there we go. We have a slight change here, and in order to see what poles 0 pair we added to the root locus, let's try to use pzmap if I provide hold on. Or yeah, let's provide hold on, but don't use pzmap. Let's plot directly on top of the root locus and use the minus c val here, comma 0, and say that this is basically, let's have, I don't know, a blue circle with line width 2, and the same for the p-val here. Should be this. Since I know what z-val and p-val are, I know that on the x-axis it should be negative z-val and negative p-val, and on the y-axis it should be 0. I can directly plot them on here. So I can see that adding them here does change it a little bit, and I want to prevent the effect of my pole 0 pair as much as I can, because I don't want to change the root locus so that I don't change the transients here. I only want to update my steady state behavior. So let's try a different value. Let's increase, for example, p-val up to 10. Let's see what happens. I can see now that the change is a bit more dramatic because the red plot was is the updated one and the black one was the previous one. So this has some effect, and you can see in the domain where I want to design my controller, uh, it has effect. Now, if I want to design a very, very slow controller, that might be still usable here, but remember that we had 30% zeta, so 30% overshoot and the zeta for that, a low one, so there is quite a difference here. But it still might work. But the best solution would be to have a small p-val, because as you can see, the effect here will be hopefully minimized, but it's still not enough. I can still see some potential here. Maybe I should use an even smaller p-val, so closer to the origin. The pair should be closer to the origin. Now you can see that the more I get closer to the origin, the better the approximation or the updated root locus looks like. So it will still have an effect, I can't prevent that, but I want to match these branches as much as I can. So this one hopefully should work as expected. Now let's use even smaller p. And you can see I have directly matched them. So the previous root locus and the root locus now is almost the same. But I have a pole zero cancellation near the origin. So I should be basically a bit more safer than this. It's not really safe to add a pole and a zero near the origin because perturbations or model errors would affect this, and I might end up in the right half plane, which is not desired in terms of stability. But it seems like this is numerically a one solution that I can be happy with. So this also concludes our design. So in the time domain, you can see that I did just use the equation here, and I've chosen a small, relatively small p-val, and that's always the case. Use a pole zero pair in the vicinity of the origin, near the origin, so that you don't affect the transients too much. And that's basically it. Now I can go ahead and define my controller. Let's get rid of this part. So I know what the controller should be. The controller is defined as, so if I want to include this here, I have to define the controller as one z-val and one p-val. So ts2 then would be, so I had this one here, let's make ts3, let's define it 3, and yeah, this would be basically it. Let's have step ts comma k, ts comma ts2 comma, let's say red, and ts3 comma blue. So we can see that of course our blue one, or a new one, has messed up the step response. So there's a big difference, but let's see what the ramp response looks like. So times, so we somehow deleted it, interestingly, but yeah. So add the integrator to have the ramp response. So that we have, hold on. It seems like we don't need it, but yeah. So we can see that they are, so the red one and the blue one is quite close. So almost identical, but there's a better gap than this one. So we have to plot t here, and therefore we used plot here. So let me quickly use plot here. So y comma t, where t is defined between 0.01 and 10 seconds, have the step response for ts, and not even ts, but this times ts. So let's plot this. So plot t comma t in magenta with mine with 2, and then plot t comma y for ts, but let's use ts2, by the way. Let's use it with black, and then ts2 for red for the frequency domain, ts3 for blue for the time domain. There we go. Let's see. Now we have a better plot. We forgot to provide comma t. There we go. Now we are talking. Now we can see that in the transients that the black one was the initial p-type controller that we've used, and then the red one was the frequency domain approach, and then the blue one is the time domain approach, and this is basically the reference signal. So the red one and the blue one are closer to the original input, and the black one is basically the p-type controller design. So the transients change a little bit. We have oscillations in the step response, so we can see that they carry on to the ramp response. So it seems like we have to have a bit more, a bit higher value for P, so that we can see now, it seems like it's still a bit too oscillatory. Did we forget to? I guess not. So okay, this should be almost the same. You can see that the controller defined with using the frequency domain and the time domain are present here. Now, of course, arguably the time domain approach is not optimal because we didn't check if, for example, the pole zero map looks like the p-type controller approach, but if you're looking for one working controller, then the blue one gives you that. It's easier to come up with a controller using the time domain, but the frequency domain approach has a better result for this special case. It changes with the plant, so you should be validating that. But if you're on an exam, you should maybe get a result, and that is most probably okay with it, because the way of the algorithm that you've used in your design is important here. But if you have time, of course, you should try to look for the closed loop and look what the result is. But this is the way of using the time domain approach and the frequency domain approach to design a lag controller. It seems like the frequency domain is more appealing in terms of the results. And the time domain is still usable, but should be optimized a little bit. So that's basically it for this question.